Hi students, in the video you can see this is the long form of periodic table, that is the modern periodic table. It consists of four main blocks. Which are the four main blocks? It is S block, that is the groups 1 and 2 belong to S block because the valence electron enter the S orbital. Then we have the groups from 3 to 12 where the d orbitals are being filled up, and so they belong to D block. And the elements in group 13 to 18, they belong to P block as they valence electrons enter the p orbital. Then of the periodic table, you find that there are 14 different elements lying in between lanthanum and hafnium. In the sixth period, in between that of group 3 and 4. And these elements are known as lanthanides and they belong to F block. Along with the actinides, the 14 elements lying in between actinium and rutherfordium in the 7th period. So these both belong to F block because the F orbitals are being filled up here. Have a closer look at the elements in group 13 to 18. You find that these block of elements will consist of metals at the lower part. Diagonally, you find there are elements which show both the properties of metals and non-metals. So they are included under semi-metals or metalloids. And we have the different elements in the upper triangle which are mostly showing the non-metallic character. All these elements are constituting the P block. So in P block you find a variety of elements are there which includes non-metals, metalloids and metals. Group 13 to 18, you find that the p orbitals are filled up in the valence shell. Group 13 elements are called boron family. Group 14 elements are known as carbon family. Group 15 elements are known as nitrogen family or pnictogens. Group 16 elements are known as oxygen family or chalcogens. Group 17, they are called fluorine family or halogens. Group 18 have several names. It is known as the rare gases, inert gases, noble gases. It is also known as group 18 elements, and since it has zero valency, it is also known as zero group elements. So we shall see in detail about group 13 and group 14 first. As mentioned earlier, group 13, 14, 15, 16, 17 and group 18 elements belong to P block. We shall now see which are the elements and what will be the general electronic configuration of P block. So take the case of group 13. The first member is boron. Then we have aluminium, gallium, indium, and the last element, that is nihonium. Shall we write the electronic configuration? Boron has atomic number 5. So the configuration is helium, 2s2 2p1. Then aluminium has atomic number 13. So this will have the configuration neon. Then 3s2 3p1. Next one will be 31, that is gallium. Gallium, the next noble gas will be argon. So it will have 18 electrons. Then we have 3d10. Then we fill 4s2 and 4p1. Hope it is clear. Then the next one which has the higher electronic configuration, will be that of krypton. Then similarly 4D10 will be filled, followed by 5s2 5p1. And the next one is thallium with xenon configuration. Then we have 4f14 5d10, then 6s2 6p1. Likewise, you can fill up the next one. So here you find that instead of xenon, we have radon, and the configuration becomes 5f14 6d10 7s2 and 7p1. So on examining the valence shell, you find that it is 2s2 2p1, 3s2 3p1, 4s2 4p1, 5s2 5p1. So general electronic configuration can be written as ns2 np1. Hope it is clear. The next group is carbon family. The first member being carbon, then followed by silicon, germanium, stannum, lead, and flerovium. So the configurations will be similarly helium, 2s2 2p2. This one will follow the configuration neon, 3s2 3p2. Germanium will have the configuration argon, 3d10 4s2 4p2, followed by tin with the configuration krypton, 4d10 5s2 5p2. Next one is plumbum with the configuration xenon, 4f14 5d10 6s2 6p2. Flerovium will have the configuration radon, 5f14 6d10 7s2 and 7p2. So what will be the general configuration for this group? You find that it will be following the configuration ns2 np2. Hope it is understood. Now similarly, you find that group 15 will have the configuration ns2 np3, followed by group 16 with the configuration ns2 np4. 17th will have the configuration ns2 np5, and the last one will have the configuration ns2 np6. So group 13 has the configuration ns2 np1, which can be written as ns2 np1. So what all oxidation states are possible by these elements, that we will see. In group 13, the valence electrons are 3, and so the group oxidation state will be +3 by removing all the 3 electrons. Also have the oxidation +1. By removing 1 electron, it will get some stability. The two different oxidation states are +3 and +1. Now consider the case with group 14. We have the general configuration ns2 np2, which can be written as ns2 np 2. Here, the group oxidation state is got by subtracting 10 from the group number. So you get group oxidation state as +4. What are the other oxidation states? You see that from this, if they remove 2 electrons, it will become somewhat stable. So the other oxidation states are +2. It can also become stable by gaining 4 electrons, 2 here and 1 each here. So total 4 electrons can be accepted. So when it is accepting electrons, it will get -4 oxidation state. What are the different oxidation states for group 14? You have +4, +2 and -4. In P block, thus we have the group oxidation states for the different groups as +3 in group 13, that is 13 minus 10. Then we have the 14th group with +4 oxidation state, that is the group oxidation state. Group oxidation state of 15 will become +5. Likewise, group 16 will have +6 oxidation state. Group 17 will have +7 oxidation state, and group 18 will have +8 oxidation state. On checking the valence shell electronic configuration, one is able to understand that in ns orbital we have 2 electrons, and np you find that only 1 electron is present in 13th group. So you find that it can also show +1 oxidation state. Now take the case of group 14. We have the arrangement with ns2 and np2. So group oxidation state, by removing all the 4 you get +4. It can also become stable by losing the 2 unpaired electrons, so it can also have +2, or it can again gain 4 electrons and become stable, so it can have -4 oxidation state. Coming to group 15, we have ns2, np3. So what are the possible oxidation state? By losing all the 5, it becomes stable. By losing 3, it becomes stable, that is +3. It can also become stable by gaining 3, that means it can also have -3 oxidation state. Coming to group 16, we have the configuration ns2, np4, 1, 2, 3, 4. How will it become stable? It can either lose all the 6 electrons, gaining +6 oxidation state. So the easier method of gaining stability is by gaining 2 electrons. So that means it can have -2 oxidation state. It can also have +2 oxidation state, or it can even have +4 oxidation state. By losing all the 4, somewhat stability is attained. Take the case of group 17. We have ns2, np5. So here it becomes stable by losing all the 7, or it can lose all the 5, become +5, or it can gain 1 and become stable, that is -1. Halogens can also show some extra stability by losing 1, that is +1. It can also lose the 3 becoming plus 3. So you find that a variety of oxidation states are shown by halogens, and that is mainly for large size halogens which are less electronegative, and so you find that is mainly shown in interhalogen compounds. In the case of group 18, on the other hand, we have Ns2Np with 6 electrons. So you find that this is completely stable. So you find that it doesn't have a need to join with others, or you find that the valency is said to be 0. So in such case, the oxidation state possible is 0. That means it has less tendency to combine with others. A unique behavior is shown by p block elements. So you find that in p block, the variety of oxidation states are seen. For example, if you take group 13, you find that the group oxidation state is plus 3. So it can show a variety of oxidation state plus 3 and plus 1. Hope you have understood, plus 3 and plus 1. And when in the case of group 13 elements, you find that plus 3 becomes less stable as we move downwards. So when we reach the heavier elements like indium and thallium, the oxidation state plus 1 becomes more prominent, and this happens because of a shielding effect that is caused by the d orbitals or d electrons, due to which the s orbitals remain as an inert pair. So this property, it is known as inert pair effect. So what do you understand by inert pair effect? In p block, as we move down the group oxidation state become less stable, and you find that the lower oxidation state, that is 2 less than the group oxidation state, becomes more stable, and this happens due to the reluctance of the s orbitals in unpairing and taking part in bond formation. This process we call it as inert pair effect. So, in group 13, thallium plus 1 is more stable. Similarly, when we check group 14, you find that the group oxidation state is plus 4, and as we move down, it becomes 2 less than the group oxidation state. That means lead and stannum, you find plus 2 becomes more stable. And why it becomes more stable? Due to the poor shielding effect of the d orbitals that are making it, s orbitals reluctant to unpair. So we find that in group 14, lead will have plus 2 oxidation state, which is more stable. Coming to group 15, we have the group oxidation state as plus 5, but as we move down, you find that plus 5 becomes less stable. In the case of bismuth, plus 5 will easily change to plus 3 because of the reluctance of the s orbitals in unpairing, and you find that it will be having oxidation state 2 less than the group oxidation state. So bismuth is always having plus 3 oxidation state instead of plus 5. Same trend follows for group 16 and 17 as well. So you find that the group oxidation state of oxygen family is plus 6, and you find the heavier members will show 2 oxidation states 2 units less than the group oxidation state, and this happens only for the heavier elements, and this is due to the poor shielding effect of the d orbitals that are involved, and you find that the s orbitals are reluctant to unpair, and thus resulting in inert pair effect. So tellurium will show only +4 oxidation state. However, inert pair effect is absent in the case of group 18, because you know that group 18 elements are generally inert in nature. Only the xenon will form compounds with fluorine. So that will be learned in detail in the next class. Thank you.